In this lesson, we will discuss reaction rates and reversible reactions. Chemical reactions proceed at different speeds. Some reactions take a very short time to occur. For example, white phosphorus ignites spontaneously when exposed to oxygen. Other reactions take place very slowly, for example, the rusting of iron. Quantitative analysis shows that most reactions slow down as the reactants are used up. Rate of chemical reactions are important in our daily lives as they are to industrialists and chemical engineers. Industrialists and chemical engineers are interested in obtaining products rapidly and easily and as cheap as possible. Therefore, to achieve these reactions can be accelerated so that they are economically viable. In this lesson, we will discuss the rates of chemical reaction and factors that affect them. The time that a reaction takes place is of great importance to the chemist in an industry. If the rate of reaction can be increased, more products can be manufactured in a given time and hence lower the cost. In cases where a certain reaction takes place at an explosive rate, it is necessary for the chemist to be able to control the speed of that reaction. Hence, it is essential for the chemist to know how various conditions can affect the speed of a reaction and how to speed up the reactions or slow down. Laboratory examples of very fast and moderately fast reactions. The following video clip shows a very fast reaction and a moderately fast reaction. Click to play and observe what happens carefully. In experiment 1, as soon as the two reagents come into contact with each other, a white precipitate of silver chloride is formed. This reaction takes place very fast. Experiment 2. A yellow deposit slowly appears. This is due to deposits of sulfur. It takes a longer time for the product to appear compared to experiment 1. The rate of the reaction is the rate of change of an amount or concentrations of a particular reactant or product per unit time. Reaction rate equals change in amount of substance divided by time taken. Different reactions have different reaction rates. Some are very fast, for example, burning of magnesium and burning of charcoal, while others are slow, for example, rusting. Collision theory states that for a chemical reaction to take place, particles, for example, ions, molecules, must collide in favorable orientation and possess more than a certain minimum amount of energy. This minimum amount of energy is referred to as activation energy. The smaller the activation energy, the faster the rate of reaction, and the greater the activation energy, the slower the rate of reaction. Reactions can only start when the reactant's energy is equal to the activation energy required to start the reaction. Collision theory and activation energy explain why the exothermic reactions do not occur at room temperature. Collisions must be energetic enough to surmount the activation energy barriers. An exothermic reaction is self-sustaining when it has started. This is because energy evolved makes more reactants to have activation energy. During this type of reaction, more energy is produced from the formation of new bonds than the energy needed to break the existing bonds, and therefore there is surplus of energy. For an endothermic reaction, energy, in form of heat or light, has to be absorbed, making it difficult for the reactants to have activation energy. This deficiency in energy has to be made up from an external source. The method chosen in the laboratory to measure the rate of the reactions must make use of a change that is taking place in a reasonable amount of time. The change should be measurable in terms of volume in case gas is produced, change in mass of reactants and products, time taken for a given mass to disappear, and time taken for a certain amount of precipitate to form. You will now learn about the factors affecting rates of reaction. To investigate the effect of concentration on the rate of reaction, click to play the video and observe what happens carefully. The table below shows sample results obtained from this experiment. The graph below represents the concentration of sodium thiosulfate used against time for the cross to disappear. From the graph, the higher the concentration of sodium thiosulfate solution, the less time taken for the black ink cross to disappear. From the collision theory, increasing the concentration of reactants increases the frequency of collision between reacting particles. The greater the number of collisions, the higher the rate of reaction. The following experiment is carried out to investigate the effect of temperature on the rate of reaction. Click to play the video and observe what happens carefully. The following shows sample results that were obtained. The graph below shows effect of temperature on reaction rates. The curve shows that the time taken for the completion of the reaction decreases drastically with the increase in temperature. The rate of reaction increases because the velocity of all reacting particles increase as the temperature increases. This increases the kinetic energy of the particles. Increase in kinetic energy provides the particles with the necessary activation energy required for the reaction to occur. For this reason, many reactions in industry are carried out at high temperature to get better yield. The following video clip was carried out to investigate the effect of surface area on the rate of reaction. Click to play the video and observe what happens carefully. Calcium carbonate reacts with dilute hydrochloric acid to form calcium chloride, water, and carbon 4 oxide gas. The carbon 4 oxide gas escapes through the cotton wool to the atmosphere. The cotton wool stops the acid spray from escaping during the chemical reaction. A graph of loss in mass in grams or mass of carbon dioxide in grams evolved against time is shown below. Loss in mass is faster for powdered marble and slow few large marble chips. This means that the rate of reaction is faster for marble powder and slow for large marble chips. The more finely divided the solid, the greater the surface area. The following experiment was carried out to investigate the effect of a catalyst on the rate of reaction. Click to play the video and observe what happens carefully. Before manganese 4 oxide is placed into hydrogen peroxide, the solution gives off oxygen slowly, but not enough to relight a glowing splint. When manganese 4 oxide is added, the reaction becomes vigorous and oxygen is given off within a very short time. The oxygen is now enough to relight a glowing splint. The mass of manganese 4 oxide before and after the experiment is approximately the same. Manganese 4 oxide acts as a catalyst in this reaction. It increases the rate of a chemical reaction but remains chemically unchanged at the end of the reaction. The following equation shows the products formed. If 3 grams are used instead of 1 gram, the amount of oxygen of a given time would be more. This being because of the large surface crew, which would improve its efficiency. However, the volume of oxygen gas produced would be the same. The graph of the volume of oxygen given out against time with and without a catalyst are shown below. A catalyst provides an easier path by lowering the activation energy of the reactants, allowing the reaction to proceed faster. The graph below shows the activation energy of the reaction with a catalyst and without a catalyst. The table below shows some catalysts and the processes they are involved in. Study the illustration shown below to show the effect of pressure on gas particles. Pressure is significant in reactions involving gaseous reactants. When pressure increases, the volume in which the particles are contained is reduced. This brings the particles closer, thus increasing collisions and affects the rate of reaction. When the pressure decreases, the volume increases, creating more space for the particles, hence reducing the rate of collision and consequently the rate of reaction.